Welcome to the session on projectiles, review exercises. The objectives for this session are to review previous topics through exercises, namely, use the constant acceleration formulae to solve problems involving vertical motion under gravity, and manipulate trigonometric ratios. We will now solve the review exercises shown on your screen. Pause the video and have a go. Press play when you're ready to view the solutions. Now recall the standard notation for an object moving in a straight line with constant acceleration. Remember that s equals the displacement, u the initial velocity, v the final velocity, a the acceleration, and t the time taken. We now also have g, the force of gravity, which is 9.8 meters per second squared, but this takes the place of acceleration. Recall also the formulae that we introduced in the last two sessions. Let's now take a look at an example. Pause the video and have a go. Press play when you're ready to view the solutions. So here's what's happening in pictures. A ball falls off a shelf and then bounces up and down. So let's take a look at example 1a first. We are required to find the time the ball takes to hit the floor and the velocity on impact. We're going to take the downwards direction as the positive direction. So when the ball falls off the shelf, we have the initial velocity as 0 meters per second. Gravity or acceleration is equal to 9.8 meters per second squared. The distance it travels is 1.5 meters, so s equals 1.5 meters. We are required to find the time the ball takes to hit the floor, so t. We're also required to find the velocity, but let's take a look at time first. In other words, we have s, u, and a, and we are required to find t. So we are going to use this equation, s equals ut plus a half at squared, because it includes all of these values, or these letters. So let's solve this. We're going to substitute in all the values into this equation. We have s equals 1.5 here, u equals 0 here, a equals 9.8 here, and of course t remains as it is. Tidying up and rearranging this equation gives us that t squared equals 3 over 9.8. So t is equal to 0.3 seconds. We're going to ignore the negative value of t, as time, of course, is not negative. Now let's find v. Again, we're going to take the downwards direction as the positive direction. So we have s, u, and a, and we are required to find v. And therefore we are going to use this equation, v squared equals u squared plus 2as. And plugging in the values into this equation, we have v, because we're looking for v, we don't know what it is yet. U equals 0, a equals 9.8, and s equals 1.5. And calculating gives us v squared equals 29.4. Therefore, v equals 5.4 meters per second. We're going to ignore the negative value of v as travel is in the positive direction. Now let's attempt part B. We are required to find the maximum height above the floor after the first rebound. Notice we've highlighted something else in this example. We've highlighted the fact that the ball rebounds with 3/5 of the speed with which it strikes the floor. We've noted from the previous part that the velocity is equal to 5.4 meters per second on impact on the first bounce. Therefore, the return velocity is 3/5 of this, therefore 3/5 of 5.4 meters per second. And this equals 3.2 meters per second. So let's solve this. We have on the next part of our journey that the initial velocity is 3.2 meters per second. We have that g, or acceleration, is equal to 9.8 meters per second squared. And we have that the final velocity, v, is equal to 0 meters per second. And we would like to find the maximum height, s. So we have u, v, and a, and are required to find s. Therefore, the equation we are going to use is v squared equals u squared plus 2as. So let's plug in the values. Here we have v equals 0. Here we have u equals 3.2. Acceleration, or g, equals minus 9.8 because now we're treating the upwards direction as the positive direction. And finally s, the distance, which we are trying to find. Therefore, rearranging this, gives us that s is equal to 0.5 meters. Now let's take a look at the next exercise. We are required to write expressions for x and y in terms of v and alpha in the diagram shown. So let's solve this. By trigonometry, we have that sine alpha equals opposite over hypotenuse, so we can plug that in, giving us opposite, which is equal to x, and hypotenuse, which is equal to v. So we have sine alpha equals x over v. We also know that cos alpha equals adjacent over hypotenuse, so we can plug those values in as well to give us adjacent, which is equal to y, divided by hypotenuse, which is equal to v. And so we have cos alpha equals y over v. We can rearrange this to give us x equals v sine alpha and y equals v cos alpha. Now for exercise 3. Given that cos alpha equals 11 over 13, we are required to find sine alpha and tan alpha. So let's solve this. Here's our right-angled triangle. Here we have cos alpha equals 11 over 13, so adjacent over hypotenuse. and the opposite of alpha is x. We can now solve and find sine alpha and tan alpha. Since we have cos alpha equals 11 over 13, we have that the adjacent is 11 and hypotenuse is 13. By Pythagoras, we can find the missing side to give us x equals the square root of 48, as shown here, which equals 4 root 3. Therefore, given that sine alpha equals opposite over hypotenuse, we have that sine alpha equals x divided by 13, which equals 4 root 3 divided by 13. And now for part B. We know that tan alpha equals opposite over adjacent. Therefore, we have that tan alpha equals x over 11, which equals 4 root 3 divided by 11. This brings us to the end of this session. If you have understood its contents, you should be able to use the constant acceleration formulae to solve problems involving vertical motion under gravity and manipulate trigonometric ratios. Thank you very much for listening.